Hawkins? Anyone? No? Okay. I just want to say this, I didn't want to put this in the end because I'm not an expert in this field that I'm going to talk about. A lot of work has gone in this field. I just want to get the credit upfront before I talk. Almost all the content is from the JVM mechanics given by Doug Hawkins. It literally opened my eyes. I've been doing Java since 2005, so probably 10 years, you can call it a decade. There are a lot many things I learned after going through the presentation, so I decided, even if I copy the presentation, I'm going to make every slide myself and share. That's the only way I get to internalize what these guys are talking about. Hopefully, you will feel the same and go see the original presentation, but here is my question. Okay, so another raise of hands. Tell me how many of you have written, or at least you think you've written, single-threaded Java app. Single-threaded. Few, 10. Everyone else always multi-threaded, is it? Okay, cool. And who thinks Java is faster than C, just for the language wars? One. Okay, I'll count 2, 3. Others disagree? Okay, we'll get there. I don't think I can do a full screen because that's affecting the sharing, so I'll leave with that. I'll take that, all of us write Java applications and put things in production. Have you heard of things like warmup? Do you warm up your production apps? Have you heard of this? 1, 3. Do people know what is a warm-up? It's a literal term, warm-up, right? So you bring the app. If it's a shopping cart app, you do a bunch of shoppings, maybe with a dummy session, so that things are all hot in place. Ever heard of it? You can make it interactive. Yes, no, no, some yes. Okay. So in case if you have done warm-up, I'll assume you have. That's the pattern, right? So if your application will start slow, it will not be that performant in the beginning when it starts up. And then when you warm up, it will, things will start settling down and you will see a good performance. But let's say you open up, let's say you are building a trading app, right? So I warm up before the start of market open. The moment market opens, right, you want the performance to be peak. What actually happens is it'll be really slow, right? It'll be significantly fast when you're warming up. The moment your actual trades come in or actual shopping cart, is get hit, it slows down. This is known. If you have not observed it, go do that in the apps that you have written, and you'll be surprised. This is fact. And then after some time, let's say a minute or two, based on their application on how you have written the code, it'll go fast again, right? This is exactly how JVM works, right? So I'll come to why it is during the talk. Am I making sense so far? You can stop me, ask questions, make it interactive. Okay. Right, so I have this picture. I hope it looks like an illusion. So the illusion when we write a Java app is this. I use my IDE, I write code, I compile as a jar, fine, and it gets interpreted. That's the story we all know, right? That's what I do. I assume most of us know this, but in case I'll ask this question, how many of us know that Java gets JIT compiled at runtime? Pretty much all, right? But that's all we know. I'm sure most of us have seen this picture, right? What are you doing? I'm playing something. Why? Things are compiling, right? That's a usual, most famous cartoon. A lot of functional programmers make fun of it. All these things happen, right? Because underlying truth is, if you have to compile, it takes time, right? Imagine compiling when your application is running, right? That's what JIT means, right? Just in time compilation. You don't compile upfront, you compile when things are running. So this is practically true for JIT too, right? If you're saying compilation before you start running your app, static compilation is a time-consuming job. Compiling when your app is running is going to be even difficult. Have you thought of this before? No, I didn't either. Little bit about the interpreter, right? So JVM, I'm mostly hotspot, right? It's threaded. We all know that, right? And the name hotspot, what does it do? You have an interpreter interpreting your bytecodes, but it does one more thing, or a lot more things beyond that, right? It identifies what area of your code is hot. In the sense, it gets called again and again. Right? That's the name. That's the reason for hotspot. The reasoning behind it. And as far as hotspot is concerned, it's a method-based JIT, meaning if it identifies a method is called multiple times, it will compile it. There are other technologies like trace-based JIT, but hotspot is method-based. Good so far? Okay, so I won't bore you with all the details. We know Java, we've been doing it. I have a few examples. All these examples are in the GitHub from the main talk, from Doug Hawkins as well, but just to demonstrate. So can everybody, I don't think anyone can do that. So what I have is a simple two for loops, right? In the inner loop, I'm just creating a new object, right? That's all I'm doing. So it's going to run 250 times 1000, right? In every iteration, 1000 objects are created, and I do 250 times. That's all that happens. I'm just trying to make a point here. Are we clear with the example? Let's see. Right. I have graph output of this, so I'm just going to run it. So it starts off like the first time it runs, it takes, for the first iteration, it takes about 420,000 nanoseconds, right? And it goes on and on and on, drops to 4,000, 5,000, 30,000, 0. I have no idea. So can you ever think it's going to take 0 nanosecond to do anything? I don't think so. I don't believe that, but that's the output. Sometimes 1000, sometimes 0, and it keeps fluctuating, right? So let's go back. Right, so I plotted it. I know that you can't see this in a presentation. So what I took the output and then plotted as a graph. The big spike that you see here is our GC pause, which we all know, right? So when a GC pause happens, it pauses for a few seconds based on how much you have in your memory. And then you see things going 0. Right? It was still not clear, so I made another graph. So this time not exactly the time interval, but in the logarithmic scale. Right? I took a log of the time, and I plotted. Right? What was very surprising is that you can exactly reproduce what Doug was talking in the talk in a very simple program. So when your app starts running, it starts in the interpreter mode. Think of it as like a 10,000-ish times slower, right, than what it can be. So that's the first plateau that you see. Significant time, just to create new object, right? Does nothing. And then there's another phase where it's slightly okay, right? That portion, second plateau. And then there is a third phase where it literally says 0 time or 1000. Why this randomness is because I think most of the laptops that we have, including MacBook, does not have a resolution of 1 nanosecond. Right? So it can either give you 0 or it can give you 1000. That's the precision of system nanosecond on a MacBook. Right? So that's the reason why it was fluctuating between 0 and 1000. Literally it's saying there is no time interval. Right? It's instantaneous is what the output is. Can anyone guess why it is 0? So the code is this. Again, 2 for loops. Outer for loop 250 times, that's your iteration. Inner for loop is about 1000 times, it's creating a new object. I'm time stamping between each iteration, start of the time and the end of the time. That's all I'm printing. Any guess? Explain that to me. Yeah, so we can take a guess that. So I have to admit, right? So all this, I'm pretty sure most of us or every one of us have gone through, and we know, okay, things are getting compiled. there is something going on there that's actually optimizing things. That's the level of understanding. But can you clearly tell me what happens? Yeah. So that's actually correct, right? So because it's actually dead code elimination, right? That's what happens. But I'll come there. There is a lot more that goes in. Okay, let's move on. So we are talking about hotspot and things like that, right? So how does it actually trigger? Right. So let's say that the hotspot is triggered on a few numbers, right? So let's say I have a method and I call it 2 times. It's not going to compile for you, right? Every JVM has got a counter. Only when you cross the threshold, it's going to compile things for you. And that is a magic number. It differs from JVM. It differs from even each platform, right? Um, so the number is, let's say, if I call a method 20,000 times, you can take a guess that it is going to compile. And how do I know it's going to compile? Example 3. So don't worry about the tiered compilation for now. You can pass a JVM hotspot option flag to your Java when you run. This is available for all JVMs. If you say, add print compilation, it's going to tell you when it's compiling your methods, right? But this, I told you, compilation is slow. So if you fire up a Java VM and you do things, call 20,000 times and shut down, you won't notice that things are getting compiled because compiler takes time, right? So what I have is an empty method. That's what I have, an empty method, and I'm looping 20,000 times. But in the end, I'm sleeping for 5 seconds because I know within 5 seconds it should compile, right? This is pretty small. So if you run this, so it's telling you that, so there is a way for you to read this output of print compilation. The first column that you see, this one is the millisecond elapsed since you started the JVM, right? The second column that you see is, think of compiler as a resource that's reading its task from a queue, and every task put in the queue has a number, and that is the number, right? There are a lot of things it compiles. So everything, that is the queue. There is a detailed explanation on what these symbols mean. I'll come there in the end. And then you get to see what method, how many bytes got compiled. Clear so far? Did I lose everyone? Right. So bottom line in this point is what you need to know is if you think a method is getting called n number of times and n is greater than a threshold, it will get compiled. Otherwise, it doesn't get compiled. So if you fire a VM, do something really hot, and then immediately shut down, you're not going to see the benefit. It will never be CO. You will incur some clock cycles. You will waste something. Right, so I don't think people can notice the last line. So the last line here says that it's also compiling main. That doesn't make sense with whatever I told you so far, right? If I call a method 20,000 times, it gets compiled. Main get called once. Why did it compile it? The main is there, right? That's the last line. Any guess? Why the hell did hotspot compile main? So let's say I have another method. Yeah, you're there. That's because I told the answer. What else? Why? I mean, yeah. So
I think only if you do that, you can do the other dependency.
No, it's just an optimization thing. What entry point is right in the sense that what they call as so if you have a concept of an invocation counter, which is what we saw, which is how many times a method gets invoked. With that, you can't do much. You need another counter, what people call in Hotspot a package. Right? Package simply means that I have a code, something is hot, and I'm going back in the function. A funky way to say that I have a loop. That's what it really means. So you have another counter called package. So these two counters work together, right? So one counter alone is not enough. The main gets compiled because main has a package counter of 25,000 because it keeps going back. The code inside main keeps going back. Clear?
Is there a way to force compilation of a method if you think that's optimized, that will help in optimization?
So there is another, I'm not clearing that. There is, if you keep following what Oracle is doing with Java JDK 9, there is this notion of ahead of time compilation. Basically, it means you want to compile Java like you compile C++. Only then probably yes, but that's not the whole picture. So you should probably point you to the top. All right. So we know what is an invocation and a package, right? Move on. I used this in a previous talk. I like the picture, so I'm using it again. That's what I call on-stack replacement. So think about it. Your program is running, it is getting interpreted. Sometimes, oh, I think some method is hot, and I'm going to compile, and I have a few bytes. What I need to do from the interpreted, code in the stack, I need to replace that portion alone with a compiled portion because the rest is still not hot, it's still not compiled. You get what I'm saying? So it's not that I will compile everything for you because that's no way your app will run. It will only keep compiling forever. Right? You can ask that simple question: why can't I simply compile everything and make it fast? It's not going to happen. So there is a technique, what they call as a non-stack replacement, is that if the JIT compiler finds a portion of the code that is hot, it will swap that with the compiled version. So going from left to right is the optimization part. You can, and this happens in theory, go from compilation to the interpreted mode. That's called deopt. I'll cover that later. That's what happens in the first, the Roadrunner and the snail example I showed you. Are we all clear so far? Two counters, that's how JIT does it. Okay. So I was talking about loopback, right? So if I go back, so in the end, I'm sorry, I should have thought through that the font is too less. What it means is only the portion of the main where you are having that loop is getting compiled, not the whole main method itself, right? They are still two different things. There is compilation for loopback, there is compilation for the whole entire method. So what triggers the whole full method compilation is again your invocation and package. I have one example. So this example, I have two methods. The first method is going to be called just twice. That method is going to call another method like 10,000 times. And we're going to see an example of a loopback compilation because outer method is going back, and the whole method compilation. Right? Clear? Okay. Where is example 5? Okay. So, can you see? Okay, so I think I didn't get the right one. So your output is expected to be, at one point of time it will say, I compile your outer method, and I also compile the loopback method. Right, so that should happen. Let me find out. Yeah. So I'm not sure. So at 113 millisecond, it actually compiled the whole method. At 114 millisecond, it thinks, oh, I should compile a part of it. So what really happens is that when things are getting compiled, you will end up in a phase where I compile something, I compile a portion of a method, now I'm compiling the whole method. So it will say that part of the method is made non-entrant, right? Means any further invocation will not go to that code. When it has like no one else entering that piece of a code, it will be made zombie. Right? So these are the two states to watch out for. Right. Okay, so given all this gap, this is still not the full picture. Has anyone programmed with Swing applets before? Java applets? Two. Right. So historically, Sun had two versions of compilers, right? As if we don't have enough problems. The first one is meant to be used for a client-side app. By that I mean graphical user interface, like applets. And then there's another version called the C2, which is meant to be used on your server. You can ask me, right? Your runtime is equally complex already. Why are you having two compilers? You still have two compilers. Right, so the reason is this. If I'm building a user app, what do you want? You're dealing with a human, right? I will get pissed off if I have to wait for like 5 seconds for my welcome screen to be painted. But I'm okay to, I will not even notice the difference between a 50 millisecond and a 60 millisecond. I'm okay with that. I need quick feedback, so you're interacting with a human, right? So that is what it was meant for. In the sense, it has to be really, really quick. The compilation speed should be quick. It's okay if it's not too optimal, right? That is C1. Now C2 is as efficient as you can get. I would actually say it is more efficient at times than your C and C++ compiler. And there is a reason, right? It's not as a language war statement. It is, right? And that's, if you actually talk to VM folks and listen to their talk, so far you would have only said Java faster than C, C faster than Java. There is a reason behind that, right? So I'll try to cover that. Right? So take it that C2 is quite slow, but is extremely efficient. Good so far? Right, so and then we are all greedy. We'll say I want best of both. Right? We say that all the time. So this was so in JDK 7 when they are coming up with that, they have made the promise what I call as a tiered compilation. So I will use best of both worlds. I build compiler is a huge investment. I build two versions. They have their own strengths, but I'm going to balance them out. So have you guys heard of tiered compilation before? Anyone? No. Okay. Right. So what it means is that sometimes I will use C1, and at times when they are really, really hot and this has to be super optimized, I will go to C2. That's the basic funda. But that's a thing. In practice, there are actually 5 states in which your code goes. Right? So the good old interpreter is how everything starts. Right? So that's your level 0. And then C1 has 3 different states. And then the 4th state is your C2. Right? Why is it that way? I'll tell you. So we talked about 2 counters, right? Your invocation and package. And you need some code. You're not writing that code. When compiler compiles it, it is actually injecting that piece of code, right? That has its own overhead. So that is your basic counters. C2, unlike your static compilers, need heuristics and profiling, right? I'll talk a little bit more what it really means. So to give input to C2, it's not enough that I just give a code of your application. The C1 is supposed to feed in lot of metrics to C2, right? Only because of this, C2 is super efficient even than a C or a C++. Right? And that comes with the cost, and the cost is roughly about 30%. Right? So you can say I can always go do that. Again, is the cost. That's why people don't do that. So the normal flow is this: I will start at level 0, and then I will immediately jump to level 3. I won't go to, I didn't say what is level 1, I'll come back. I'll immediately go to level 3, which is everything, your counters, your heuristics, every information that CD knows. And if it crosses a threshold, it will be given to the C2 compiler and you have the best compilation possible. That's your normal flow. But let's say that you have a lot of code and your C2 is super busy. Right? That happens. When C2 says that I'm too busy, don't feed me more tasks, C1 will fall back to the layered mode. From 0, it'll go to basic invocation counters and wait. If it crosses a threshold, 20,000 more calls, it will say, oh, now it's a good time to get the heuristics and profiling and all that. And then if it crosses the profiling threshold, then it will decide, okay, now C2, you have to compile. Okay, so far? Yeah. There is another level as well. If C1 thinks you're writing a very trivial method, super simple, there's nothing in there, maybe empty, maybe written 5, just a constant. From 3, it'll say I'll go back to 1. It'll take a decision that C1 is as good as it gets. There's nothing C2 is going to do more, right? It's a call that C1 makes. Are we good? So you have all these things, right? How the hell will I know is my code getting compiled in level 1 or 4? Right? Again, that question is there. So you can, this is example 4. Show you what I have. Okay. Yes. So because the behavior changes from 7 to 8. In 7, tiered compilation is off by default because they were working on it. In JDK 8, tiered is on by default. So if you're using JDK 8 in production, you are using a tiered compilation in runtime. So C1 is in play, C2 is in play, and it's studying. If you want to have like a repeated execution, just say plus tiered compilation, so it works same in 7 and 8. And I'm going to print the compilation, right? So what do I have? So I have a simple method. I loop 3,000 times. I know it's hot enough for C1 to compile. Then I sleep for 5 seconds because I have to wait for C1 to get over. And then I loop 20,000 times again. I know for sure that this method is too hot. C2 should pick it up. Right? That's the whole idea. Let's see. Yes. Right. So when you run with a tiered compilation and you are using print compilation as an option, you will see these numbers. These numbers are the ones that I was talking, 3 and 4. Right. So you'll see 4 here that says that flash buffer is getting compiled because I'm using system out print and then I'm printing out a lot. Yeah. So you see this. You see this line. Where is my send compile? Yeah, so so this is the part where at, let's say 5,000, about after 5 seconds, the sum method is getting compiled at level 4, right? If you go up, you should see sum method getting compiled at level 3. And then this is what happens. If you have a more optimized version than what you had from C1, at some point of time the compiler will say, what you actually compiled with C1, it's no longer valid, and I was telling about made non-entry. Right? That's what happens in the end. C4 is ready with your method, and what happened with C2 is ready. What you compiled with C1 is obsolete. It throws away. So by now you should have a picture that a lot of compilation happens when you run your Java. This is something you don't You don't actually realize when you run or usually develop your app. Right? Your app. Any questions so far? Before I go? I think, sorry, I didn't actually fill this. Have people heard of this term called save point? Save point. Never heard? Yeah, that is true. So, if you are running Java, we all know Java has GC process. Yes? Yes. You can imagine, right? Let's say that most of us said we are writing multi-threaded apps. So let's say I'm having a multi-threaded app, right? Imagine for a second. Your app, you're doing crazy thing with your classes and objects and states and whatnot, right? Connecting to socket and doing something. How on hell is GC going to do compaction? How on earth is GC going to inspect when things are running and going to take, like, let's say, intrusive decisions, right? It has to. It has to compact, it has to edit, it has to do a lot of things. How on earth will GC do that safely? There's no way you can do, right? We are talking about readers and writers, and this is the code that is completely unaware of your application. This is your JVM code. So the VM folks, this is how they've done it. I think every now and then in your code, every now and then, if I'm right, is for every 2 bytes of your Java, there is a poll that happens. Can I go to a save point? Can I go to a save point? Can I go to a save point? Keeps happening. You never know that. Right? And there's another, I think this is a too detailed topic. I didn't put too much content there. So the point I'm trying to make is this: watch out for your save point in your app. If you have a lot of save point, the time to save point is also, you can find that if you enable diagnostic options in your VM and say print save point, the time it beats on. So your app, when it is running super fast, it can actually slow down. You might think your DB is down, you might think whatever is down, but it's not. It's actually waiting for all threads to get to a safe point, so it can do GC process. Which is what we usually think. GC is the only things that kind of stops the world, which is also not true. Right. So I'll go back. I'll go back to the first Roadrunner and the stale example. So let's say that it's the same first program. You don't have to read the code. It's the same first program, except that I just introduce one variable. I'm calling it a trap. During the inner loop, if trap is not equal to null, I do something. If it is null, something else, right? So for the 200 iteration, it is null. So one way. And then if on the 200th iteration I say trap is some new variable, so the if is actually going to say yes, and then it's going to a different branch. What people call this in compiler terminology is called a phase shift. Your program is functioning one way, suddenly something happens, your if check or whatever external reasons, it takes another course, right? Your typical branching. So let's see what happens. If I run it, it's going to be very hard for you to plot. But this is what happened. This slide there is what happened when I simply changed the variable from not being null to null, and it was so far the compiler thought, this variable is always null, and I'm going to optimize for that. Right? JVM does this all the time. I don't know other compilers do this. Probably yes. So it will make guesses. This is for sure what your C and C++ does not do, because C and C++ is statically compiled. It has no way to know this object is always null at runtime. They don't know that, right? Whereas your JVM knows it because it's interpreting. For 200 iteration, your object is null or not null. It will not optimize the other part of the code. It will not even compile that. It will only put a trap. If the trap is set, this is what happens. So this happens. Let's say, I as a C2 compiler made an assumption that you're always taking one path. but I have a code to just in case you take another path. When that happens, your compiler code is wrong because the way it compiled is, let's say, too aggressive. Right? C2 is very aggressive. It will throw the compiled code. It will bail back to your interpreter. Interpreter can interpret anything, right? Whatever if branch, because it is interpreting. It's an REPL. It's an interpreter. So this is what happens, and this is called. This is one example of deoptimization. So what is the difference between a warm-up and a production? If you are in a trading app, you'll be warming up. I'm sure when you're warming up, you won't be sending trades to the exchange, right? Because there will be one if somewhere that says, if the sender is from a test user ready, don't send it to the exchange. But when you open it to the actual stock exchange, that user is not test user. It will go to the exchange. One if will trigger and it will change the branch. Guess what? Your jet didn't know that. It didn't compile for that. It bails back to your interpreter, and interpreter is 10,000 times lower. That's why when you warm up, so you warm up, if it is 100% guaranteed to be your production code, then you're good. But most of the warm ups I think is not so. Like, if you are having a banking app, you won't be debiting money from your account really when you're warming up. So that happens. But over time it will catch up. Then it will know that okay, there is a branch, I should not optimize this, and it goes faster. And examples. Right, so going back to the first, why is it 0 and 1? So this is what happens. C2 it has various techniques under its right? It has exactly your dead code elimination. So it will first find out that your new object, there's nothing there. You're doing a for loop with an empty. I won't compile anything. So what you're timing is 2 nanosecond call. Because your timer is of precision of 1000, you'll either get 0 or 1000. That's what happens. Okay. Right. Okay. So I just want to cover. So all of this is static. If you have a static analysis of your source code, you can take this call. You don't need heuristics. You don't need a JVM for it. Where your JIT really shines over a static compiler is the speculative optimization, right? Speculative is what I just said, the first thing, right? If a condition is always true, I'll optimize only for that, not for the else part. If the else part has to be true, then I'll mail back to the interpreter. You know that. This also happens for the null check, right? Everyone is aware of null pointer. I won't embarrass you asking. But when C2 compiles, it is not going to do an F check on a null. Any idea how? Let's say that if you are having an object, index off, right? Your array is empty or null, whatever. If your compiler is not going to make an if check, then how is your code still correct? So this happens. So VM is written in your C++, not in Java. So in C or any program where you have pointers, if you write null to an address, any C programmer here? C. Right, so you write null and you're going to get a core dump, you're going to get a set fault, right? Because you can't do that. So what does C2 make? It does not do an if check. If an object is null, that's too costly, right? The compiler will actually take your object. It will do one instruction called move to a fixed address. Right? So if that object happens to be null, it will actually throw a seg fault. But because it's happening inside a VM, there is a seg fault handler, and that will be caught, and it will throw null. This is what really happens. It can do all this, but if it checks that this is going to be too costly, you are seg faulting a lot, and there is again a number for it. There are too many magic numbers inside a JVM. If you really want to know what they are, if you fire up Java and say XX print final flags, it will print a lot of tables full of numbers. So if it thinks that you are doing a null pointer a lot of times, it will not do this trick. This is one of the speculative optimization. The other one we talked about, which is your phase shifting, the common thought. You can really ask why on the hell should VM do all this trick? Or can it not simplify? It's because not one optimization is really useful on its own. If it can predict a branch is always taken, that adds to an inlining, that adds, so different techniques build on top of each other, and that's what gives you performance. That's the reason why even if it is a really small technique, you don't see too much benefit in isolation. That actually adds up and you will see a significant benefit. Right, so there is still a lot more. For example, if you have an abstract class and you have only one implementation of that abstract class, it's all good, but it'll all be compiled good. The moment you actually load in your JVM the another version of abstract class, the whole thing actually goes for a deoptimization because it doesn't know about the class. Right? So takeaway is there are more than one ways in which you will deoptimize from your compilation to an interpreter, which will make your Java go slow. Alright. So I just listed, so if you are into using Java for really high performance, low latency throughput apps, there are a bunch of things that you can watch. So if you really want to measure your latency, there is this, if you have not heard, Gil Cheney, he's the CTO founder of Azul. He's written an excellent tool called histogram. If you want to measure latency, that's probably the way you should measure latency. There is a tool called JHiccup. If you want to know how much hiccup your app is having, you can profile that. There is a brilliant tool called JitWatch. Basically, if you're not comfortable with JVM flags in the command line, I'm better off with the UI. Then JitWatch is your choice. It will tell you graphically. I've not used it much, but it will tell you graphically what is going on, which is getting compiled, which is getting in line, all that you'll get to know. And then there are tools, work and work2, they are your Apache Bench AB replacement. If you're using AB to do your load testing, that's after some point you're testing AB and not your app. So you need the tools like work and work2. I can send the link. You can go. Right. So that's all I had. I just like that Twitter. Someone tweeted saying if you like a speaker's talk, instead of saying awesome, say what you learned. Any questions? I'm happy to take. Yes, that's a very good question. So we keep preaching, right? So write smaller methods, and if you ask somebody a question, why? The best answer that you've got, it's more readable, right? That's not true. If you're having smaller methods, you are actually hinting to JIT that it will do inlining. There is a threshold on what a JIT can inline. Do we know what is inlining? Okay, I'll say in case people don't know. So let's say I have two functions. One function calls the other. If the second function is literally very small, like a getter setter, then you think, oh, I don't need an overhead of calling another function stack push pop argument. I'll take the code in place replacement in the parent function. That's in your inline. Why is it so useful? Because when you inline, you can actually, there is a lot of techniques like common subject function elimination, loop unswitching. You can do a lot of optimization. Inlining is the mother of all optimization. To answer your question, JIT will only inline if the method is, let's say, less than 9 bytes. So if you have smaller methods, they are candidates for being inlined. If a method is too hot, and there is a threshold again, if you run print final flags, you will get to know that number. It will inline. So in theory, writing small methods is good for reading, is also good for speed because JIT will inline for you. It will only inline if it is hot. Hot by definition of your package, invocation, all those notices. If it is not hot, if the method is too big, You should actually go and play around. Not lot you can grab in a talk. Just add print compilation and it will tell you. If you want to know what is getting inlined, it's not just one flag. There are a couple of flags you need to enable. Like uninstall diagnostic option, and you say whatever count equal to 1, it will tell you what is getting inlined. You can actually read that statically. You run and you wait for some time before your Java shuts down. You'll get to see what is getting inlined.
Yeah, out of so if there's a dependency injection, how does the whole optimization turn out?
It is no different. Your dependency injection is just walking down a tool. It may be funder for an app, but with JVM it's all the same. Let's say I have a class, and okay, in the talk he actually says that that's the last thing that he touches upon. If you are running a JVM and you're using a third-party jar, and by mistake you didn't do that in the class path, every time JIT gets compiled, it will think it is there. It's not there, it will wait. So the same thing for a J. I know your dependency. It's more of walking down the path. DI is only an app level magic. There's nothing in the JVM that actually affects anything. If I'm right, you can check.
What about other languages on the JVM? Do they have a similar way of compiling?
So I initially gave a talk of, so you think you know JVM, but I changed it to Java. It's a JVM thing. The Scala, I think people look out for so many flags of this, right? Inlining, print compilation, so on and so on. It's a JVM, it's not your language.